Hi everyone, welcome back to my channel. So as you have seen from the title, we're going to apply LSTM today. You might have heard this a lot recently since it is very famous for analyzing text data. But there's a growing interest in using LSTM for forecasting, such as forecasting sales or forecasting temperature. So in today's video, we're going to try to predict bond yield rate using LSTM. Let's study together. So before we dive into the modeling, let's talk a little bit about bond yield. Bond yield is a return that a bondholder could expect to get every year. So for example, if a government issues a bond, let's say 10-year bond, and then we buy it and we put it at home, never sell it in a bond market. For every year, for 10 years, we would get some amount of money, and that amount of money is a percentage of our initial investment, or some would refer it as face value. That percentage is called the yield rate. Now, this yield rate might change every day in the bond market, and knowing the yield rate would be very useful for many people, for investors, for the public, for the government, because bond yield is an economic indicator which could tell us the economic activity of the issuer country. In today's video, what I mean by the issuer is the US government. So knowing the bond yield could tell us about economic activity of the US. So yes, what we're looking at for today is US bond yield rate. And to get that data, we need to go to the official website of the United States government, as you've seen here. So the website is home.treasury.gov, and after landing on this page, you click on the Data tab and then click Daily Treasury Par Yield Curve Rates. And so here's the data. So yeah, the data is provided only in a year basis. So we cannot ask for a specific period, such as August 2022 to August 2023. We cannot ask like that. And for today's video, I think I want to look at the look at the bond yield data from 2018 until now, which is August 2023. So what I need to do is to click 2018 for select time period 2018, and then click apply. And then we will get the data only for 2018, starting from January to the last day of 2018. And then you should click download CSV. And then you would need to repeat that for 2019, 2020, and so on. I've downloaded that beforehand, so yeah. Anyway, let's look at the data set for a second now. So the Department of Treasury of the US offers several kinds of bonds, from shorter terms, like 1 month, 2 months, and some of them are longer ones, like 10 years, and then 20 years or 30 years. In this video, we're going to focus ourselves with the 10-year bond yield data. So this column here. Okay, and I want you to look at the date column as well. So here, January 2nd, and then January 3rd. So yeah, where's the January 1st then? So the data included here is only for business days. So the website won't provide you with a weekend price. Okay, so when you download the data and you check the number of rows in the data set, you would see that you won't get 365, but around 250 rows. So if you look at the data set in this website, you would see that the dataset is sorted in ascending order, so that the oldest data is at the top row. But you can try downloading and see it for yourself that the downloaded dataset is sorted in descending order. So that's why in this pre-processing code, we would have to sort it again. Sorry, I didn't mean to copy it. So we would need to sort it again. Anyway, okay, so now that we are in our PyCharm, and these are the libraries that we would need. And this is the pre-processing code block. So after downloading several dataset CSV files, we would need to combine it, concatenate it into one big file. And this code block is showing you how to do it. So for starter, I load the earliest dataset, which is the 2018 yield data, and then sorting it. And then I print here just to tell us, so we can know for sure how many days exactly, how many business days are there in 2018. Okay, and then for the other files, I would put them in the for loop so that we would repeat some of the routines several times. So we would first read and then load it and then sort it right away based on date. So this would sort it in ascending order. And then next, we are printing how many days. Since I saved the file name according to date, so I always include the year, sorry, not the date, but the year in the file name. So I would ask the library RE to extract the numbers, to extract the year. So yeah, that's what this part of code here for. And then lastly, we concatenate with the older data frame DF. Actually, this could have been, so the 2018 dataset could have been put in the for loop as well. So yeah, you can try modify this to get a more concise code. And then after getting out of the for loop, we would get one big data starting from 2018 and ending in August 2023. And then to make our analysis easier and faster, I decided to save it into CSV beforehand with this name, full daily treasury rates 2018-2023 into a CSV file. And this is the file that we're going to use from now on. And if you print, it's around 1,500, if I remembered correctly. It's around that. Okay, so I'm not going to run this code block, but I'm still showing it here just for the sake of transparency and reproducibility. Okay, so that's how we get the data, the full data. Now let's talk about LSTM. I'll try to explain that just briefly though. You can find many better, a lot more in-depth explanation about this. So yeah, first of all, this slide here, I got it from DeepLearning.ai. So DeepLearning.ai offers some courses on deep learning and machine learning, and I took some courses from them, and one of them is sequence model, and Andrew is the instructor of that course. So yeah, that's how I get this slide picture here. Okay. So LSTM is a part of neural network. So neural network is a group of neurons, and each neuron would process the data to get either features or to map input to output. And there are several types of neurons to process different kinds of data. So tabular data, for example, tabular data could be processed with the basic neurons. And then there's a group of neurons which could process image data. And then there's another group of neurons which could process and analyze sequence data such as text, audio, and time series like point yield here. And the network for sequence data is also different from the others because they use recurrence, so that the output of the first neuron would be the input of the second neuron, and the output of the second neuron would be the input of the third neuron, and so on. Neural network that falls in this group are GRU, and then LSTM and RNN. We're going to just focus ourselves in LSTM. This rectangle here, this big rectangle here is the LSTM neuron. So what makes it different between LSTM, GRU, and RNN? The difference between them is what happened inside the cell, inside the neuron. Okay, so this is the LSTM neuron, and it takes three things. The first one is xt here, which is the data itself at time step t. So t would be 1, 2, 3 up until t. And then it also takes c, which is memory cell of t-1. So it is the memory cell from the previous time step. And then it also takes a. You can think of a as the coefficients. So the coefficients from the previous time step. Okay. And it will also output three things. The first one is the yt is the output, and then the memory cell of that time step, of the current time step, and the coefficient of the current time step. Okay, so taking a and x, taking the coefficients from the previous time step and the input data of the current time step, we could put it into the forget gate, where this function would be calculated, and getting out of the forget gate is the forget constant. Forget constant is telling us how many or how much of the memory cell from the previous time step you want to forget, or well, you can think of it too as how many of the memory cell from the previous time step you want to retain. So the forget time step would be used to be multiplied with the memory cell from the previous time step. And then let me change the color, and then still using a and x, the coefficient from the previous time step and input from the current time step, you could get the update constant here. And the calculation of the update constant is done in the update gate. It's here. So the function here, if you look at this, it's quite similar, really similar, in fact. It's just difference in the name of it. So it's a sigmoid function here. So it's a sigmoid function of the matrix W. The matrix W is obtained from multiplying the A and X. And then after getting the matrix W, you would add it with the intercept B. Okay, and then using A and X again, A t-1 and X t again, you could put it into the 10H function here to get the candidate memory of the current time step. So the candidate is denoted with a tilde. So the intuition is this: you have the memory cell from the previous time step, and then you get another data. After getting a new data, you would create a new memory, right? The new memory is in the C tilde of T. And then you want to combine the current memory and the previous memory. So that's what happened here. So that's how you get CT. It's here. It's a combination between the memory of the current time step and the memory of the previous time step. And yeah, so that's why we need a constant it's like the proportion of the memory that you want to retain. Okay, so this is the update constant and this is the forget constant. And then one more thing, we also need to get our coefficients. We need to sort of like updating our coefficients. And to get that, we still need our AT minus 1 and XT, and then put it into the output gate here. Put it into the output gate and doing this calculation on the left, and we will get an output constant OT. And then what we multiplied with? We multiplied with the CT, the memory cell of current time step. So the memory cell of the current time step would be put into the 10H function, and the result of that would be multiplied with the output constant to get 80. So it's the last equation on the left side. Okay, and then what else? Now, the only thing left to do is about YT. So from the coefficient of the current time step, you put it into a softmax function, and that's how you get your YT, your output. And so this only happens in one time step. Each layer would have several time steps because, first neuron, second neuron, third neuron. But how long do you want it to be? What is T? So in other words, we want to determine the T by ourselves, and we can do that like roughly approximate the number of T by looking at the time plot. Okay, so here we are back in our pie chart. Now we want to make our time plot. So first of all, we need to load our CSV file, the full dataset that we've provided earlier. And the parse date here, because I want Python or pandas, in this case, pandas to see the date column as the class or the type date time. And since we're focusing ourselves with the 10-year bond, that's why I decided to make a specific variable called Y10, year 10. And it's just a column of the data frame 10 year. And then to make the time plot, you only need one line actually, which is line 24 here. And then the x-axis is the DF date, and then the y-axis is the yield rate. And the rest of them, like from line 25 to line 27, you only annotate it actually, give the title and then the y label. Since the yield rate is in percentage, so that's why I give it as percentage. And then you can just show it. Okay, so here's a time plot. Before the pandemic, you see that the yield rate is around 2.5 until 3, well, maybe almost 3.3, I guess. And then in 2019, it started to decline to around 1.5%. And then when pandemic hit, it dropped sharply to less than 1%. But then it started to rise again, have its up and downs until now. So at least from 2018, the bond yield rate in recent days are at its highest level at around 4%. Okay, so let's try to zoom in this. Okay, so we see that the x-axis now is moving in monthly. So this is 2023 May, and then this is 2023 June. And you see like there is a pattern, like two small cycles, even though each cycle doesn't made of the same amount of days. So like this is the first cycle and this is the second cycle. Even though it's not always like that. So for example, like here, 2023 June to 2023 July, we have many up and down. So yeah, it's not always true like that, but I noticed some patterns like that several times. So like this, 2022 December to 2023 January. It has this part and then going sharply. And then like this, 2022 July to the next month. It's like there's one cycle and then another cycle. It's a very loose interpretation though. Based on that rough exploration, I thought, here's what I'm thinking. I thought maybe we need just 10 units of LSTM, since LSTM neurons earlier. So because 10 units would make of 10 days, and 10 days in this dataset would make 2 weeks, 10 business days, 2 weeks. So I guess because one month is made of 2 little cycles, and let's just assume that each cycle takes 2 weeks. So that's why I want to have a window series of 10 values, and then we want to predict the 11th value. And like that. And by the way, the last day of our data set, I don't know if we can still zoom in. Oh yeah, okay. So here, this is the last data point that we have. It's in 2023, August 21st, 2023. You can check that by yourself. And August 21st, 2023 is on Monday. So I thought I want to make a prediction of bond yield to the end of August. So we still have 8 more business days to complete the data. So I thought maybe, yeah, it could be fun to predict the whole 8 days ahead, just to see how the bond yield would go as August is closing. Okay, so the next thing to do is to prepare the data set again. Why do we need to do that? Because we need input and output, right? Like for example, in house price regression problem, we would predict the price of a house based on several features such as total rooms, such as the location of the house, or the age of the house, and so on. So you would have a matrix of inputs and then a vector of the output. But with time series, what is the input? What is the output? Especially if we have only one series as our ingredient to the model. So that's why we need a window size. That's why I said, oh yeah, okay, let's set the window size to be 10. So the input would be the first value to the 10th value, and then the output would be the 11th value. So we window our time series, our long time series, to be like that. And then we shift our window so that the input would be the second to the 11th value, and then the output is the 12th value. And we do that again, we shift our window again so that the input would be the third, would be from the third value to the 12th value, and the output would be the 13th value, and so on. And even though we can do that, well, with just for loops and NumPy, I want to show you how to do that with TensorFlow. But don't worry, this is how you do it with the TensorFlow. But yeah, I will also do it with for loop for forecasting. More on that later. Okay, so yeah, to prepare our data in TensorFlow, let's set the variable, the constant, let's say, the window size to be 10 and the batch size to be 32, because in deep learning and neural network, we tend to train the model in batches of data instead of one huge data set. It's for stability, and it's for, we get a better performance that way. You can learn more about that if you read the theory of training neural network. Okay, so yeah, first of all, we should change the type of our series from Panda series to TensorFlow dataset with a function here from tensor slices. So if you look at Y10, the definition of Y10 here, it's a column of DF, and DF is a pandas data frame. So if you take one column of it, it would be a series, pandas series, and yeah, that's the type of Y10. And you want to change the type, to convert the type from pandas series to TensorFlow dataset. But it's still a long dataset. It's still a long series that you have of 1,500, like that. And so to window that, to take windows of our dataset, we need the window function. And the window function takes some arguments. The first is the size of the window, and then the shift and drop remainder. Drop remainder means that if, for example, we have 10 data points, and then we want to windows it every 5 values. The first window would be 1 until 5, and then 2 until 6, and 3 until 7, so on. And then when you start your windowing from the 7th value, you would have only 4 values. If drop remainder is false, TensorFlow would take 7, 8, 9, 10, and then not available, NA value or NA value. But we don't want that. So drop remainder true would make the windowing stopped at the 6th value. So 6, 7, 8, 9, 10, and then that's it. There will be no NA values, no missing values in our dataset. And then Now the windowing size. Why is it window size +1 when I said over and over that we want to have 10 units, 10 data points before predicting the next one? So here in line 33, we window the data sets for input and the output in one go. And then later in the next lines, we will separate it. Okay. So what's coming out of this window, the window function? We will have a data set of data sets. Data set of data sets. Let's see. Return a data set of windows. And windows itself, the type of window is also a data set. Okay. So it's just a data set of 11 values in our case. 11 values and then 11 values, 11 values, so on. And we have so many of that. Okay. And then since we have many data sets, we want to flatten them. And we do it with the flat map function. And flat map is essentially a function that is applied to each data set, to each of the 11 data points data set. And so we need to make up some function to each data set, and then the result would be flattened. So actually this lambda here is just a workaround to get a flattened data set. That's it. So since we have 11 data points in our window data set, if we batch all of them, we will still get all of them, right? We won't lose a single value. And then not losing every single value on each window and then flatten it. So yeah, what we get from this line is a data set of data set. A data set with several rows. Like that. Okay, and then the next thing, this is where we separate the input from the output. Okay, so map is actually applying a certain function to each row of our data set. Okay, see, across the elements of this data set. Elements in this case is the row. So on each row, we take out the output, which is the last element of the data set, and we take the input. Oh, sorry. No, I mean the other way around. So the input, the x, well, not the x actually, the input, the first 10 values, and then the last value as our output. We do that function to every single row, and what we get from this line, from line 35, would be a matrix of input, a matrix of several rows times 10 columns, and then a vector of output. Okay, so shuffle here. It's a good practice to shuffle our dataset to avoid bias. And then lastly, we have batch and prefetch. So batch is, so right now, up until line 36, we have a huge dataset. And now we want to batch it with batch size 32 so that the training would be easier. Tensorflow would batch it for us. And then prefetch here is also to aid training, to make it faster. It's like while the model is training one batch, it's taking one batch to standby, so that when the first batch is done training, the next batch could start training right away. It's like that. Okay, so yeah, that's it. That's the data set. And now we can do the model building now. So to build a model, to define the model, we are going to use the sequential class, meaning that the input would go through the first layer here in line 41, and then after that go through the next layer, LSTM layer, and then go to the dense layer and then get the output. The input would go through the layers in a sequential manner. That's what we're doing here. So in the first layer, we have a lambda layer, and in the lambda layer, we expand dims, meaning that we just add another dimension to our data set. This is for preparing the input to get into the LSTM layer. Since the LSTM layer requires an input with 3 dimensions. The first one is the patch, and then the second one is the time step, and then the next one is the number of features. Since we're dealing with univariate time series, so we have only one feature, and that's why we can just add the dimension with expandim's function at the end of the axis, at the end of our dimension. Okay, and then after adding a dimension, we go into our LSTM layer. It's a simple neural network since we have only one layer of LSTM, and the total unit to make a layer is the window size. I set it to be equal to the window size, which is 10. So there will be 10 rectangles that you've seen earlier in the slide picture to make a layer. And then the output of that would be a vector of 10 values. Since you know that in each rectangle, it would output a value. So that's why we have 10 rectangles, we have 10 neurons. So we have 10 values as an output. And 10 values, to get from 10 values to 1 value only to our prediction, we do so with the dense layer. Dense layer with just 1 unit. Okay, so that's our model. And then before training it, we should compile it. I set the loss to be the mean absolute error, and then the optimizer to be SGD. And then, yeah, that's it. We could fit or do the training to the model. I set the epochs to be 100. So I want to go through the full data set 100 times. That's what it basically says here. And then, yeah, this is the data set. So X here is already including the input and the output. So that's why we have that X. Okay, so the verbosity is just setting how I want it to be printed out. And I set it to be 2. Okay. You can check out the documentary of TensorFlow for knowing about these arguments. And then I want to, the result of the training would be stored in history. And history is an object, and it has a history component, which is a dictionary. So if we want to get access to the loss of this training, the error, we get it by doing this. The key of the dictionary is loss. And then this is just making the plot of the loss curve. And then, yeah, let's just show that first, run that first. We'll see here in this console how the loss is decreasing as we go further into our training process. Okay, so it's already starting its training process. It's epoch 1 out of 100. Yeah, so as you can see, the loss is getting smaller and smaller. 0.1 and then 0.08. Okay, so while waiting for our training, let's go to the forecasting first. Okay, so I will explain about the loss curve in a moment. So for forecasting, we will have new data. So I'm pretty sure that we will have some data from our time series that is not included in our training. Okay, and so that's why we're taking the last 10 values of our time series, and that's what we're going to use for predicting the very first day. And yeah, so that's the starter of our new data, the first 10 values. And then I want to store the predictions in a list called prats. And then since we want to predict 8 days, so from the first until the 8 days ahead, that's why I set a variable and ahead equals 8. And then for I in range 8, so we're going to do this for loop 8 times. We will slice the data, the new data here, to have 10 values. Okay, and then this line here, the sliced data would have only one dimension, which is the time step. And so we need to add another dimension, which is the batch number. And since we have only one batch, because we only have one observation, right? So we can do so just by doing adding numpy new access. That's the way to get input to have 2 dimensions. And then that's how we let the model to predict the input. And then the prediction that we get is a matrix of 1 row and 1 column. So that's why, well, not a matrix actually, but it's not an array either. It's not a scalar either. So that's why we need to index it like that. So anyway, the predicted data would be appended to the new data, so that the new data now, at the first iteration, it will have 11 data points. You see, so at first it has only 10 data, but after the first iteration, it will have 1 additional data. And then we store the prediction again to the prats list. And then we will print it. Okay, so the training has been done now. Okay, so here is the loss curve going from the first iteration to the 100th iteration. So yeah, as you can see, it goes down. It dropped to almost 0 in just a few iterations. So let's zoom in. Okay, so at first it takes, the loss is around 1.6, a little bit more than that, but it takes only 5 iterations to get less than 0.2. And I guess the error since then fluctuated like that. Let's zoom in again, zoom out again, and if we look at this, yeah. So the final MAE is around 0.1. Okay, so let's continue our code in predicting. So after we print our predictions, we want to plot our predictions. So I'm going to plot the predictions alongside with the original data, so we can see in what direction is the predictions going. So if you look at it, this is a predicting process. Okay, and here are the predictions. So 4.24, yeah, it's around 4.26 for like that, stays around like that. A little bit caveat though, I have to be honest that the forecasting seems to be different every time you run it. Because the last time I ran this, it's not predicting this number. But yeah, let's see. Okay, so yeah, here's the data again. I forgot to label the y-axis here, but you know, it's the percentage, right? And yeah, if you see the predictions is denoted in pink line, it's around here. It's very little because it's only 8 days compared to 1500 days. Okay, so based on our model earlier, we predicted to be going up, the bond yield to be going up. Actually, I haven't seen the real data as well. Yeah, it's not even the end of August yet as I'm recording this. So yeah, I can only wait and I'll update it. Maybe in shorts, in YouTube shorts, I'll update it about how is this going. Is it doing a good job or not? Okay, one little caveat here. The x-axis for the predictions is not that accurate actually. So you can take a look at the x-axis only for the training data, but for the predictions it's not that accurate because or is it accurate? Well, no, not accurate because there's supposed to be some gap here because we are taking 2 weeks actually. So it's supposed to have like Tuesday, Wednesday, Thursday, Friday, and then some gap, and then Monday, Tuesday, and so on until the last day of August. But it didn't do that because I didn't make a data frame of predictions actually. I only make a list of predictions, right? I didn't set which predictions is referred to which date. So yeah, I could improve that. That's the area that I could improve. You could try to modify the code yourself and maybe share it with us in the comment section. Okay, so that's it. That's it for today's video. Thank you so much for watching, and please subscribe to my channel, Timely Time Series. All the code that I have presented here will be uploaded in my GitHub. It will be available in my GitHub by the time this video is uploaded. Okay, so I hope you enjoy this video. Thanks again so much for watching, and thank you for subscribing if you haven't done so. please click the subscribe button. And yeah, so I'll see you next time. Bye bye.